everyone. In this video, we are going to discuss the Stork enamine synthesis. So this synthesis is kind of going off of our Michael addition discussion. So previously we saw that we can have a doubly stabilized enolate. So this would be a Michael donor. And then we saw that we can just have a regular enolate, which is not as stable. Now remember we said that a more stable or weak nucleophile will perform 1,4 addition. And then a stronger, less stable enolate will perform 1,2 addition. Or at least 1,2 addition will be favored. Now, if we try to form, for instance, the following, like we did last time, we're going to get really low yields because, again, this would be the 1,4 addition product. And so this would have low yields. So how can we form this product using that starting enolate, which would actually favor 1,2 addition? Well, there is another option. We could use an enamine. So similar to an enolate, if we look at an enamine, it does have a resonance structure. Where we do end up with a negative charge on a carbon. Now, that negative charge is not as strong as the negative charge on an enolate. So let's write not as strong as enolate. So this can act as a Michael donor. So that means we can do 1,4 addition reactions. So let's show, oh, whoops, I got my slides mixed up. So let's show an example where we can use that starting ketone. We're going to actually turn this into an enamine using a secondary amine. And then we'll use that enamine to perform the 1,4 addition. Okay, so let's show the enamine that we would form here. It'll look very similar to the one we just drew. And let's just draw that resonance structure again, just for good measure. Just to get some practice in. Okay, so now this is our weak nucleophile. Now we're going to attack our alpha beta unsaturated ketone. And because this is a weak nucleophile, this will attack the carbon 4 position. So we'll end up with that 1,4 addition product. All right, so this is our intermediate. So in the next step, we're going to add acid and water. So not only are we going to protonate our oxygen to make our enol, which will tautomerize to a ketone, but we're also performing hydrolysis on the enamine to reform our original ketone. So let's just make a note that we're performing hydrolysis on enamine to get back our ketone. And then we're also going to form our enol, which will tautomerize to the ketone. So now our final product is that 1,4 addition product that we saw before. And now it's the major product instead of the minor product. Okay. So again, going back to our original slide here, we had tried a problem where we used this enolate, and we saw that we got a mixture of products. We had the 1,2 addition product and the 1,4 addition product. And because this enolate was less stable, the 1,2 addition product was the major product. But what if we want to form the 1,4 product as our major product? Well, instead of using LDA, we can actually use our secondary amine in acid, and that will give us an enamine, which will then give us the 1,4 addition product as the major product. So these are things chemists have to think about because, sure, we could produce a little bit of our desired product, but ideally we'd want to produce a lot of our product that we want. So we might have to take some extra steps to get there or think more creatively about it. All right, so this was a shorter video. In the next video, we're going to wrap up this chapter. We're going to talk about Robinson annulation and then some synthesis strategies. So I will see you then.